This is a lecture style presentation. The lecture is online at that link. It is also linked from the breakout sessions page on the conference website. So you will have all the slides, you will have all the code that we're talking about here. And what I'm hoping to do today is to go through code snippets in a fairly leisurely fashion and talk about what the code does, but you have complete working examples linked from every slide. And if you find that one of those examples is not working, please do let me know, because things change periodically. Everything that we're going to talk about is also a Codelab. So I'm going to exit out of here for a second, go to the code editor. And if you go to Help, User Guide, there's an EDU tab, which is a newish tab. We've had this stuff hidden before. You go to the educational resources, and for some reason it's not loading my directory. There it is. Lab 6, time series analysis, is hands-on practice of everything that we're going to do in this lecture. So if you want the self-paced, hands-on version of this lecture, feel free to go to the Docs, EDU tab, and scroll down in that in this directory listing here to Lab 6 time series analysis, and that's where all this stuff lives. Disclaimer, this is not a statistics course. I am going to be presenting some statistical methods here, and I assume that you have the requisite background to use these methods in Earth Engine effectively and not for nefarious purposes. So, in the interest of the statistical background, should you want it, it is in this free online textbook. The reason I chose that book, there are several reasons. One is that it's free. Another is that it's short and sweet. And lastly, Shumway and Stauffer wrote a really great paper that I like about Kalman filtering or Gaussian linear models. I think that was in the 80s. Anyway, it's a great paper, so I have a lot of respect for these authors. And they have this great book. So the examples that I'm doing here are largely taken from this book, and I reference equations where possible. Okay? What this course is about is time series analysis in Earth Engine. And specifically, our time series is Landsat 8 NDVI. And as you will see in a moment, it's a messy or a dirty time series. So there are missing data, there are noisy data, clouds get in there despite cloud filtering. There are still cloudy data points, so keep that in mind. When I made this slide, there were 64 images, and I think now there are about 25 more. So this is not the series keeps growing as more images are acquired. So of course, you can limit your analysis to specific time intervals just by filter date, but we're going to use the whole series and just let it grow and see what happens. I'm going to present a framework for analysis using join, map, and reduce. And everybody in here should be fairly familiar with what those terms mean in the Earth Engine context. Specifically, joins are the way to combine data. Map is an overloaded term, and in this context, I'm using it to mean applying the same operation to every element in a set, as opposed to the capital M map, which is the geographic map display that you see in the code editor. And reduce is the way to aggregate things in Earth Engine, so getting statistics. So wherever you see reduce, you can almost substitute statistic. The examples that I hope we're going to be able to cover in here are linear modeling over time, harmonic modeling over time, auto-covariance and autocorrelation, and cross-covariance and cross-correlation, and maybe auto-regressive models, time permitting. But that stuff gets real crazy, and so we'll see how it goes. Okay, so here is our time series. Landsat 8, NDVI, irregularly spaced points. So this is about as dirty as it gets in terms of how you want to analyze a time series. Irregularly spaced points, there are missing data here, for example, where we've done cloud masking. And there are also noisy data. So if our cloud mask failed, we get a nasty cloud or cloud shadow data point in there. And this is reality, right? We all deal with time series like this, especially when time series exist in every pixel, which is how things work in Earth Engine. So this is just one pixel here. And when we do time series analysis, in fact, we're running these models in every pixel. And hopefully that will become more clear in a second. And again, you can see where these images are from. But if you run the code links at the bottom, you'll see the series up till now. And it's sort of fascinating to see how things change, which is why I've left these images in there. So you can compare the charts that you see in the code editor to what's in these slides. And the difference is the result of another year's worth of data. By the way, stop me at any time if you have questions. And when you ask a question, remind me to repeat it, please, for the camera. I will forget. Okay, here's our time series. And the first thing that we want to do is just fit a linear function. You know, is NDVI increasing over time or decreasing over time? So in this example, I sort of cheated by using the visualization API. So when you make a chart, you can customize the chart by adding a linear trend to it. And that's where that red line comes from, is the charting API. And I believe that should be in the example. But what we want to do is compute it. So what does that mean? Specifically, what we want to compute are the betas in this very simple linear model. So here, P stands for pixel. And in this example, let me just get my red pointer here. In this example, it's NDVI. And T is just time. And we might want to measure that with different units. And the little epsilon or lowercase e here is just a random error, which will creep into our time series. Now, as I mentioned a second ago, when we fit this model in Earth Engine, we get betas in every pixel. So as I mentioned, these time series exist in every pixel. And that's how you evaluate these models. So the first thing that we want to do is add the variables that we need to the images in the collection. So specifically, we can compute the date. So in fact, I did this, I'm noticing right now, I did this the long way. You can just say image.date if you want. But this is the long way. Maybe your date field is not stored in the system:time_start property, in which case you can always get the date this way. So this is more general, actually, but there's also image.date function. And now I'm doing something pretty arbitrary, which is just computing the time in years and year fractions elapsed since 1970, January 1st. The reason for this is because the time in Earth Engine, which as I mentioned a second ago, is usually stored in the system:time_start property, is in units of Unix time, or epoch time, which is milliseconds since midnight, January 1st, 1970. So I've just converted that into years by computing date.difference. What do we have? We have our image, and we're going to add NDVI to it. So just normalize difference on the image with these bands. And I'm going to rename it NDVI and cast it to float. And then I'm going to take the years variable, which again is fractional years since 1970, rename that T and cast that as well. And lastly, add a constant. So adding a constant here, so when you say eeimage.constant1, this makes a constant image in which every pixel stores a 1. So this is analogous to adding a column of 1s to your design matrix in something like R or MATLAB or your statistical software of choice. So that's it. This is the dependent variable, and these are the two independent variables. And once we've mapped this function over the collection, each image will have all the variables that we need in it. So let's just name them. And specifically, the independents are going to be this list, which has the band names of the independent variables, constant and T, and the dependent variable, which is this string storing the NDVI band name. And now we want to compute the trend. And specifically, we want to reduce the time series with the linear regression reducer. So we're taking a whole stack of things like this, and we are reducing them to a single image which stores the betas for this model. It's worth noting that the linear regression reducer expects the bands in the image to be in a specific order. Specifically, it expects the bands to be in order of independent variables followed by dependent variable. And so that's why we put them into this, enforce that order here by doing a select. And when I do select, I'm just making use of the add function on a list, which is going to append NDVI to the end of this thing. So then we have a list of the band names in the proper order. Now we say reduce and linear regression, and what the linear regression reducer wants to know is how many independent variables you have and how many dependent variables you have. And so we're just telling it the number of independent variables we have is the length of that list, and the number of dependent variables we have is 1. So those are the arguments to the linear regression reducer. Okay, what comes out of this thing is an array image. And if you were in my arrays section yesterday, you will know what that means. And if you were not, I have another arrays section tomorrow. But let me explain it to you briefly right now. An array image doesn't store pixel data in multiple bands. It stores instead a vector or a matrix or an array in each pixel. And we don't want an image full of little arrays. We want a regular multi-band image in which each band represents one of the betas. So first, we go from a 2x1 matrix in each pixel by calling array project. And then we go from a length 2 vector in each pixel to a multi-band image in which each band stores the beta coefficient. So what array flatten is expecting is a list of lists. One list for each axis of the array that is in that output image. And again, we have only one axis. It's the betas in a little vector. And so we're just telling it, what do we want to name the bands that come out? And we're just going to give the bands that come out, or the betas, the same name as the variables. So the betas are going to be called constant and t for beta 0 and beta 1, respectively, according to that model. Questions about this?
Besides coefficients, what else can we access?
There is a, what is it? I think it's called residual. And the residual stores the root mean square residual of the regression, from which you can get R squared. And I probably should have an example for that, but if you search the forum for R squared, you will find my example for that. Computing R squared from those residual, from that root mean square residual.
So pretty much this image array has bands. I mean, it's a multi-band kind of thing.
Yeah. So it's a multi-band thing, and each band happens to store an array in each pixel. Yeah. Other questions? Okay. So we fit our linear model, we have our betas, and something that we might want to do with that linear model is use it to detrend our time series. And what do I mean by that? When I say detrend, I mean that I'm going to subtract the fitted value from the observed value. And so we're going to turn a time series that looks like this into something that looks like this, and the main difference is that now you will note that our time series is centered at 0. So depending on your assumptions about the time series, this is a very low budget, for lack of a better term, way to enforce stationarity on this series. And if we assume that the mean changes over time with that trend, and this is essentially a linear series over time, we can detrend this thing by subtracting that linear model and saying, okay, the result is now detrended, so the mean and the variance are the same everywhere and so forth. That may or may not be the right assumption. In fact, it looks kind of wrong here, right? But we're gonna get into the weeds with that in a second. And for now, just assume that we want to detrend this thing. And how do you do that? So first, we're going to map a function over our collection of images. We're going to select the dependent variables, and we are going to subtract image select independence, multiply coefficients, reduce sum. This whole thing here, this line, is like applying the betas to the independent variables, adding them up, and that's your linear model. So again, select the independent variables, multiply the coefficients, and reduce the result by taking the sum. So this is the same thing as beta 0 plus beta 1 times time. Or it's beta 0 times 1 plus beta 1 times time. So that's what this line does. And we're going to subtract that from the dependent variable. And then we'll rename it accordingly and just copy some time properties over. Questions about that? Okay. So that's just a warm-up. And now we're going to question our assumptions. So previously we said, oh, this series can be accurately modeled by this linear model over time. And now we're saying, no, no, no. that assumption is incorrect. In fact, what we think is happening is that there's a harmonic model over time. And what I mean by that is just by looking at this series, I'm postulating that there is a single cycle per year that represents this data set. And that annual cycle represents vegetation phenology. So for example, a deciduous forest that has leaf on and leaf off stages over time, or maybe an agricultural field that has this pattern of annual change from green to brown. And we'd like to capture that in a model. So here's what that model looks like. Specifically, it has 3 fundamental components. There's a constant term, which determines the sort of base greenness of the pixel, if you will. There's a linear term, which represents this linear change over time. So that's like the beta 1 coefficient on t. And then there's this harmonic term in red, which is this annual cycle, so 1 cycle per year. And the blue dots that you see in this little chart are the original data points. The other thing I'd like to point out here is that this red harmonic model has an amplitude, and it has a phase, and the phase is relative to the first of the year. So the time at which this thing is peaking is the phase of that function, which might be important if you're looking at something like crop type or forest type. Okay. If you recall your trigonometric identities, which I never do, I have to look them up. But what you will find is that a harmonic function of this form with the number of cycles per year is omega, which we're going to assume is 1 here. And it has a phase phi and an amplitude a. And you can decompose this thing into 2 terms, a cosine and a sine term, each of which have the same number of cycles per year, and time in radians here. So we've just converted time to radians. And now you'll note that we have linearized this single harmonic function with a phase and amplitude into 2 harmonic terms, each of which has a different coefficient, beta 2 and beta 3. And note that beta 2 is the amplitude times the cosine phi. Beta 3 is the amplitude times the sine of phi. And so we can recover the amplitude. It's the length of that vector, if you will, or it's the square root of the sum of the squared coefficients on those 2 terms. That's the amplitude. The phase is the arctangent of the ratio between beta 3 and beta 2. And again, the omega is frequency, which we're just assuming is 1 here. 1 cycle per year. So the point that I'm making here is that now we can fit this equation. We can fit this equation with the linear regression reducer, and furthermore, we can recover amplitude and phase from the fitted coefficients. Questions about that? Okay, so let's get specific about what we mean here. Here's our pixel at time t, which is equal to ndvi at time t, which is equal to this model that includes a constant term, a linear trend, so a linear coefficient on time, and this harmonic term at amplitude a and phase phi, plus an error term. And when we linearize that, we get beta 0 plus beta 1t plus beta 2 cosine of that stuff plus beta 3 sine of that stuff, plus our error term. And this ought to look familiar because it's very much like the linear model that we just fit, we know how to do this, right? So here's the constant. Here is our linear term. Here is our harmonic term. Here is our equation, and now we're going to fit it. Here's how you do it. First, set up our list of independent variables. And that list is going to include our constant, our time variable, our cosine term, and our sine term of that harmonic function. Now, map a function over our Landsat series. Compute time in radians. So we already have time in fractional years there. Now I'm just going to convert that to radians by multiplying by 2 pi. And I'm going to return the image with the cosine term, so just time radians dot cosine, time radians dot sine, and then rename those cosine and sine. So adding the 2 harmonic bands. So if you remember the previous mapped function that we did, we added the constant and the time term. Now we're using the time term, converting it to radians, and adding the sine and the cosine of those 2 things. So same drill as before. We take the independents, we add the dependent to enforce this band order that we want of independent variables followed by dependent variables. And we operate the linear regression reducer and tell it how many independents there are just by taking the length of that list, and also tell it that there's just one dependent variable in here. So 4 independent variables followed by 1 dependent variable. Question?
Can we do nonlinear regression yet?
You mean like a t-squared term?
Yes.
Sure. So this would be simply adding, add bands t dot pow 2, I think is how that works. Anyway, I don't have the API memorized yet, unfortunately. Maybe some of you do.
Can I ask a question? Is that matter of the order of the list, like a cosine, sine, t constant, the order does matter?
The order here doesn't matter. I just put it into this order because it's easy to remember, because my equation goes beta 0, beta 1, like that. Any other questions? Okay. Yes?
I'm assuming if you had 2 response variables, then your resulting image would have in this case, a 4x2 matrix.
Correct. Yep. 4x2. It's either 2 by 4 or 4x2, I'm not sure. I think 4x2. Okay. So now we get out the coefficients. Again, this is a 4x1 array image, or an image in which each pixel stores a 4x1 array. And we turn that into a length 4 vector with array project. And then we turn that back into a regular old garden variety multi-band image by calling array project and giving it a list of band names for each axis. And in this case, we just have one axis because it's a length 4 vector in each pixel. And we're just going to give the betas the same names as the variables that they're on. And now we can compute the fitted values. And the way we compute the fitted values is, again, analogous to how we did it for the regular linear model. We're going to map a function over our series. And we're going to say, select the independents, multiply by the coefficients, reduce them with the sum, and rename them fitted values. And that's it. Questions about that?
Maybe I missed the
Yeah, so this, is there a pen tool here? I'm afraid to try to use it. I was going to try to circle something, but this whole thing is simply implementing this equation. So here are the coefficients, beta 0, beta 1, beta 2, and beta 3. Here are the independent variables. There's an invisible 1 on the beta 0. Here's t, here's cosine, and here's sine. And the sum reducer is for adding up all those terms. Okay, so there's the fitted values, and that's what it looks like. For, at least that's what it looked like at the time that I made this slide. And you guys have the new code. It might look different, better, worse, I don't know. I can't remember. But you should have a longer time series. Questions about this before I forge onwards?
I think it's not directly related to that. I just wanted to clarify, when we use the linear regression reducer, we're not able to get the standard errors of those estimated betas. Is that correct?
You could compute them. I thought I had an example that was doing that. I do have an example that's doing that. And if you email me, I will be happy to share it with you. Yeah, there's some trickery in there, but yeah, it's doable. Yes?
So second and third harmonics?
Oh, hang on, sorry. The question was, can you get the standard error on the betas? The answer is yes. If you want to know how to do that, email me. Next question.
So second, third harmonics is just we add up with the frequency divided by 2, 3, 4.
Yeah, exactly. So increasing the frequency of those cycles per year. And I also have an example for that. And if you would like to see it, I will be happy to share it with you. So the question was, can you have more cycles per year? The answer is yes. You can keep adding those terms as long as you have enough variables to compute the coefficients, enough images in the time series, then you can get those. And it's like a little sort of lightweight Fourier analysis, yeah. Okay, so here's our single cycle per year, and we're happy with that. We think that this is, in fact, a series that represents a single phenology cycle, and that looks pretty good. Now, next thing is what we'd like to do is display the phase and amplitude. And first of all, to compute the phase, recall that this is the arctangent of the ratio between the cosine term and the sine term. The coefficient on the cosine term and the coefficient on the sine term. And Earth Engine has a special function for that. It's called the atan2, or the arctangent, and 2 means in 2 dimensions. So what you're looking for, you've got some function that's spinning around the unit circle, and there's a sine component and a cosine component, and you want to know which quadrant it is, or the angle of that vector is the phase of the function, and the arctangent 2 function computes the angle of that vector around the unit circle for you. So that's what the atan2 does. We also want the amplitude, and recall that the amplitude is the length of the coefficients, if you will. Specifically, there is a function for that, which is called hypot. So if you imagine that, again, there's a vector spinning around the unit circle, there's a sine term and a cosine term, you want to know not only the angle or the phase, you want to know how long that vector is, and the length of that vector is the square root of the sum of the sine coordinate and the cosine coordinate. And that function is called hypot for hypotenuse in Earth Engine. So that's how you can get the amplitude out of here. Like I say, we have this vector. It's spinning around the unit circle. It's got a length. It's got an angle. And when you have circular data like this, it's often convenient to make use of the Hue Saturation Value model in order to visualize these kind of circular data. And here's how that works. First of all, okay, so let me back up a second. The Hue Saturation Value model is fundamentally different from the RGB model of colors. And specifically, here's a little diagram for it. Hue is the angle that's going around this color wheel. The saturation is the difference from white, and the value is the difference from black. Yeah? So what I'm saying is, and the inputs to this HSV to RGB model are bands between 0 and 1. So if you give it hue, saturation, and value between 0 and 1, what you get out is RGB between 0 and 1, and vice versa. There's also a RGB to HSV conversion, which expects RGB between 0 and 1, and what you get out is hue, saturation, value between 0 and 1. So long story short, we have to convert the phase to something between 0 and 1. And we can just do that with unit scale. We know from the docs that this is spitting out radians between -pi and pi. And so we're going to scale it between those, and that's the hue, or going around the circle, the color. So the color is related to the phase of this model. The amplitude is going to be the saturation, or the difference from white. So long vectors are going to be more colorful, and short vectors are going to be closer to white, depending on the amplitude of the annual cycle. So big changes in an annual cycle will be more colorful. And I'm going to say, never mind the value, just set it to 1. So we're just operating on the top of this little color cylinder here. Okay, so I just set value to 1 here. And finally call that model. And what we get out is this nice RGB image with each band between 0 to 1 in order, red, green, blue. And by default, Earth Engine displays float data between 0 and 1, so we don't have to operate the visualization parameters at all. It should just be ready to go. And what does it look like? Yeah, wow. I guess this is my second entry for the art project. Here we are. Here's the Bay Area. This is San Francisco. This is North Bay. This is South Bay. We are behind that annoying thing of tools right there. We're right down in there somewhere. And here's the city. This is white, so not very much of a seasonal amplitude. Here is the annual grassland, which has max greenness. Are there any Californians in the house? Yeah, so max greenness in the summertime, right? And, max greenness in the wintertime, rainy season. And I'm from the East Coast, so sometimes I get confused. Max greenness in the wintertime, annual grassland. And here's agriculture. So I don't know much about agriculture, except that it results in food, which I like. But this is a different color. So it's maturing at a different time of year. And it's colorful, so there's a big annual cycle. And maybe these kind of data are useful for you in terms of classifications or crop type mapping or whatever. So that's the harmonic model. Questions about that? Okay. Now, on to the fun stuff. What is the auto-covariance and autocorrelation of that time series, or any of the time series that we've computed or been talking about here? So first of all, let's define what that means. And we're assuming stationarity here, and that may or may not be a correct assumption. Use at your own risk. But here's how we define covariance. It is the expected value of the product between the pixel value at time t minus its expected value and the pixel value at time t minus L minus its expected value. And the autocorrelation is just the covariance standardized by the standard deviations at these two time points. So the pixel value at time t and the pixel value at time t minus L. Questions about this? Okay, sorry for this code. Last year, somebody gave me some feedback that there were not enough comments in this code. So I made the font bigger. And the reason that I do that is because if I put comments here, first of all, there's no room. And second of all, everybody reads the comments and not the code. So we're reading the code. This is a function called lag. And the purpose of lag is to get the pixel value at time t as a band into the same image as the pixel value at time t minus L. So we want these to be the same bands so then we can compute covariances and so forth. So how do we do this? We're going to do a join. And as you may know, we need a filter to be operated to define the join condition. And the filter is going to be a max difference filter. And specifically, the difference that we're looking at is the difference between the times of images in this time series. So we have an image at time t, and we have an image at time t minus L. L is for lag, and we want to somehow capture that in a filter. So the system time start property in Earth Engine is always in Unix time or milliseconds since the epoch. And so we go milliseconds, seconds, minutes, hours, and let's see, did I get that right? Milliseconds, seconds, minutes, hours, days. Thank you. Let me get another sip of Red Bull here. Okay. So days, difference in days between these two time points. And we're just specifying the same field. So it's system time start. But we don't want all the images that are ahead of each image. We only want the lagged images. So I'm going to use an AND on the filter here. And the AND, we're going to specify that the time field has got to be strictly greater than. So we want the thing that we're doing the joining to be strictly greater than the other images. So we don't want the images that are forward in time. We want only the images that are back in time or only the lagged images. So that's the purpose of this filter. And now we're going to instantiate a save all join. And the matches key is going to be images. Remember that. So each image in the collection is going to have a property called images, which is going to store a list of all the t minus L images in there. We're going to have a measure key, delta t. We're going to order it by the time field, but it's going to be a reverse chronological ordering. And the reason for that will become apparent in a second. But suffice it to say, I want the first image in the list to be the t minus 1 image, the next one to be the t minus 2 image, and so forth. So we're enforcing that ordering here. And remind me to mention something about that in a second. sorted reverse chronologically, and oh right, these are the arguments to this function, which are just going to be the same time series. So there it is, all this stuff. Yes, we talked about that. Okay, so as I mentioned previously, we are joining the images to themselves, or the collection to itself. So I've specified the same variable, which is that detrended series. So these are the arguments to this function: the left collection, the right collection, and the number of days. The left collection is detrended, the right collection is also detrended, and 17 days to get about one image per time point. So one t-1 image in that images list. So once that join is done, what we want to do, so after that join is done, for each image in the collection, it stores a property called images, which stores the t-1th image. We don't want an image with a property that stores another image. We want an image with two bands, the t band and the t-L band. And so that's what this function called merge does. And inside the merge function, we're going to define another little function called merger. And here's what merger does. It takes the current image, it takes the previous image, and it simply adds the bands in the current image to the previous image. That's it. Okay? So we get images for each image in the collection. We get our images list. We make an image collection out of it. And we iterate merger with the starting value of the image itself. So there is a lot to digest here. And let us go through this, because I believe this is the only example of iterate you will get in this entire user summit. Watch out for iterate. Some places you must use it, for example, time series analysis. But it's dangerous, so don't use iterate unless you have to. Really hardcore functioning programming people will tell you that iterate is like a crutch. You shouldn't ever have to use a for loop. But anyway, I'm relying on my crutch here, so there we go. So iterate takes two arguments, a function and the starting value. And here's our function. The function is merger, and it's just going to add the bands of the current to the bands of the previous. So when we start this thing, we're giving it the image as the starting point, and it's going to add the bands of every image that are in the images list. Okay? So let's break down what this is doing. Every image in the collection stores a property called images. That images has a list of the previous images. So it's got a list of the t-1, t-2, up to t-L images that are in that list. We want all the bands of the images in that list of t-L images to be put into the image at time t. And that's the purpose of doing all this, is that we are going to add bands of everything in this list to this image. Now, if you have variables of the same name, and we do, because we have a variable called ndvi in here, when you try to add bands of an image with ndvi in it to an image that already has a band called ndvi, it's going to append an _1 to it. And the semantics of this is that ndvi _1 is the ndvi at time t-1. And if you have more images in that list, there's going to be ndvi _1, _2, and so forth. Okay? So join the collection to itself, and then map this merge function to get as output an image collection in which each image stores the NDVI at time t as well as the NDVI at time t minus L. That's the purpose of doing all this. Questions? Okay. Now, what we want to do is know the covariance between time t and time t minus L NDVI. To compute that, we can use the covariance reducer. Okay? So here's a function to compute covariance. And it's going to take as input this merged collection. And so the images in merged collection store NDVI at time t and NDVI at time t minus L. And then you've got to tell it what band you're looking at and what the name of the lag band is as well. Okay, so you want to know the covariance between NDVI and NDVI underscore something. In our case, it's underscore 1 for the t minus 1 image, or the t minus L image. And so what we do is make this covariance function, which is going to take the merged collection, it's going to select these two bands, and it's going to map another function over it, which just converts those two bands into a little array. The reason we're doing this is because the covariance reducer requires a sequence of one-dimensional arrays as input. Yeah. So what we have here in merged collection is a sequence of two-banded images, which is not exactly what we want. We want a sequence of one-banded images in which each band stores a length 2 vector, which includes NDVI and NDVI t minus L. And that sequence of vectors, NDVI and NDVI t minus L, is going to be fed to this covariance reducer. Okay? So first of all, I'm just calling the lag band, the dependent band, which again is NDVI, with underscore 1 appended to it. Now, there is a nasty logic bug in here that got somebody who was doing my lab, and they posted on the forum, oh, it doesn't work. I changed something and it doesn't work. And what they'd changed was the lag days. So they said, my lag days are no longer 17, getting you one image. It's going to be, 50 or 30 or whatever it was. So what you get is in that images list, you get a list of things from t minus 1 all the way to t minus L. And so this name changes if you change the number of lag days. You don't want the covariance between NDVI time t and NDVI t minus 1. You want the images, the covariance between NDVI time t and NDVI t minus something, which is not 1 anymore, it's 2. So you have to also change this name if you change the length of the lag. That's the point of all that. Okay, so the covariance image is just going to be an image of this function, this covariance function here, which is going to be operated on this merged collection, and then we give it the name of the bands that we want to use. And what we get out is an array image. And as you may recall, the covariance matrix is a symmetric matrix with the variances on the diagonal and the covariance in the off-diagonal positions. We have just two bands here, so this is a 2x2 matrix in which the 0th entry stores the variance of NDVI at time t, the 1 entry stores the variance of NDVI at time t minus L, and the 0, 1, or equivalently the 1, 0 elements store the covariance between the images at time t and time t minus L. So when I add this to the map, I am just getting one of these off-diagonal elements from the covariance matrix. What does it look like? Oh, something else that I have to explain to you guys. I just explained all this. There's the variance, here's the other variance, here's the covariance. Questions about that before I show you the map? Yeah.
How about, for example, if you have no values, series that you presented has like a lag or gap, the program automatically discards that point? Or?
Yeah, so if there's no matching element, that join will not return anything. That's how that works.
But you can still do the whole calculation. So it has, you have, for example, 20 possible values and one gap. So it calculates.
It'll calculate all the ones that it can.
Yeah.
Yeah.
And the other question is on the border or the
So
edges.
hang on. So the question was, what happens when you have missing data? And the answer is the join drops those missing data. Next question.
And the second is at the edges, because you are having, for example, lag 1.
Mm-hmm.
So the first element is they're missing, or the last or the first. Are the program completing a series or just leaving those two edges out of the calculation?
If it can't do the join, those are gone. So the question is, what if the missing data is at the beginning or the end of the sequence? And the answer is the join drops those data. So you're computing covariance from some possibly incomplete set of your input data. Yeah. Okay, so here's the covariance matrix. Here's the 0, 1th element. Let me just make the point here that this exists in every pixel. You have a different covariance array in every pixel. And that's what we're about to display here. This is the autocovariance at lag 17 of NDVI. Again, this is the Bay Area. Here's San Francisco. We are off the map down in here somewhere. Here's the North Bay. Here's the Delta. Here's agriculture. Here's annual grassland. And lo and behold, what do you observe? Yeah, high covariance, especially in these agricultural fields. Yeah. Okay, I gotta go faster. Should I go faster? I'll try to go a little faster. All right, autocorrelation. As I mentioned previously, correlation is just the covariance divided by the standard deviation of the covariate 1 and the covariate 2. So we can easily compute that from this image. Specifically, we just take the the covariance part is, as I mentioned previously, the 0, 1th element of that matrix. The variance of at time t is the 0, 0th element, and to get the standard deviation, just take the square root of that. The variance of the t minus lth image is the thing at position 1, 1 of the variance covariance matrix. And to get the standard deviation, just take the square root. And then we're just going to return the covariance divided by the standard deviation of covariate 0 and divided by the standard deviation of covariate 1 and rename that correlation. So operate that correlation function on this covariance image and display the result. And I think that's the next slide. Shall we find out? Haha. So there's the autocorrelation image, and it is somewhat different because we've modified covariance by the variances of these 2 time series that are going into it. And again, I'm not sure what this is for other than an art project entry, but this might be quite useful as input to a classifier, say, or to inform some other analysis about how things are changing over time. So, questions about that? Okay. So all that's fun, but what if we want to know the correlation between, say, NDVI and precipitation? That would be interesting, right? I'm kind of curious. Tell me more. So, very, very similar setup to what we had previously. The cross covariance is the covariance between a pixel at time t and a covariate at time t minus L. Okay? So specifically, it's the expectation of pixel value at time t minus its expectation times the covariate at time t minus L minus the expectation of the covariate at t minus L. And then the cross correlation, again, is just the covariance between those things divided by their standard deviations. Questions about this? Does everyone agree? Okay. Now, the good news is we have all the code that we need to make this happen. We've already gone through all that code. And here it is. We have our chirps collection, which is rainfall or precipitation. We want to join the T minus L, and L is the chirps data are arranged by pentads. So we want to lag the Landsat and the chirps data with a lag of 5 days. And so what this is going to do, again, is it's going to store for each Landsat image a list of all the chirps images that are 5 days previous to that Landsat image. Okay? And now we want to merge the bands. We don't want each Landsat image to store a list of the previous precipitation images. We want each Landsat image to have a band that represents precipitation at time t minus L, or t minus 5 days in this case. So we merge the bands together, and we operate the covariance function on it, and we operate the correlation function on it. And that's it. Now we can display the results. And here they are. This is the, I believe that's the covariance. This is the covariance between NDVI and precipitation 5 days ago. And what does this show you? This is fundamentally a map of our selected species, because annual grasses in California are our selected species that respond quickly to changes in resources. So lots of seeds come out, and when it rains, the seeds are genetically programmed to germinate very quickly. These are annual plants. And so what you see here is, in the annual grassland, a very high cross covariance between precipitation and NDVI. Because again, these are plants that are genetically hardwired to have a rapid response to rainfall. And the agriculture, not so much, because this is probably irrigated agriculture, and so it's growing in the summertime, and when it rains, who cares? The fields are fallow or being planted or whatever people do at that time. Questions about this? Comments? Yes?
In the, when you merge the images NTVI and precipitation,
Hmm?
you're creating the bands, like saying, in each image, the 5 days precipitation lag. In each image, or is just in one image, you put all the
No, in each image in the collection, you're storing a band that represents the precipitation 5 days ago.
So how is internally dealing with the difference in resolution? Chirps is 0.05.
Yeah. Yeah, great question. Scale. Normally I try to gloss over scale in this lecture. Oh, the question was, what happens when the resolutions are different? So the NDVI resolution is different from the chirps resolution, and what happens? And the answer is scale is this very fluid concept in Earth Engine. Scale is determined from the output. In this case, our output is this image in the code editor. So what happens is Earth Engine says, okay, he's using the code editor. That means that I'm going to request the inputs in maps Mercator projection at the scale that corresponds to my zoom level. It's going to do all the computations in maps Mercator at the scale of my zoom level, resampling as necessary, both Landsat and chirps, and then it's going to show us the result. If you were to zoom out or zoom in, it will recompute everything at a different scale. So that's what's happening here. Questions about that?
Can you set the scale?
The scale is set by your zoom level.
There's no way to
So when you
scale.
sport,
There is a way, and I'm afraid to tell you what it is. So I'll tell you, but you have to instantly forget what I say. You don't want to know? You do want to know. All right. You can call reproject on these data. Do not ever call reproject. Just forget I ever said that. That's the way that you do it. The reason you have to be careful is because you can say, you can call reproject on this at 1 meter resolution and then zoom out to the whole world. And when you do that, it's going to request trillions of pixels at 1 meter resolution, and it's going to try to compute the result for you, which will end in sadness. So, strike that conversation from the record, please. Any other questions? Okay. Okay. So now we might be interested not in the precipitation from 5 days ago, but in the sum of precipitation from the previous month instead. And here's how you do that. First, we lag the collection. So we're going to store in each Landsat a list of all the chirps images from the previous 30 days or from the previous month. And now we have to change our merger function. We have to change our merge function. That's the only thing that has to change here. We're not just adding a band from chirps 5 days ago. We want to add the sum of all the things that are in that list. So here's how you do that. First, you get the list. So just images, image.get images, which is getting that list of stuff, and then make an image collection out of it using from images. And take that list of lagged images, take their sum, rename it the sum, and add that band to the image. And that's it. So instead of just merging the two bands, we're adding up everything in the list and adding that as a band instead. And then we can operate covariance on it, and then we can operate correlation on it as well and display the result. And it's not ready yet because I have a disclaimer first. And the disclaimer is a quote from Shumway and Stauffer. it is worthwhile to discuss the idea of pre-whitening a series prior to a cross-correlation analysis. The basic idea is simple. At least one of the series must be white noise. If this is not the case, there's simply no way to tell if a cross-correlation estimate is significantly different from 0. So, what do they mean by pre-whitening? What they mean is, and what they suggest in this text, is to fit a harmonic model and subtract that from the input model and do the cross-correlation analysis with the residuals. So you guys have all the tools to do that. And that's the caveat here, is that, these are pretty maps, but, you might not be able to tell. If you want to do a statistical test, you might not be able to tell if these correlations are significantly different from 0 in each pixel, unless you do this. But we're getting in the weeds here. We're in the business of making pretty maps. And so let's look at our pretty map of the cross-correlation of NDVI and the sum of the previous 30 days worth of precipitation. And this is what it looks like. Quite similar to the previous one, actually. Maybe we have an even stronger signal of the annual grassland here. Of course, you'd want to tune this for your analysis. Maybe it's not precipitation, maybe it's temperature, maybe it's not 30 days, I don't know. But now you have the framework that you can use to do that kind of analysis. Questions about any of this? Maybe I'll just, before we get into this part, in my opinion, this is really sort of getting to the power of Earth Engine, because you have all these time series that are already loaded here. You can join things together and easily do a map reduce over these gigantic time series of images and have the answer anywhere. And if you were to do this, from scratch, it would be hard. And so I think these kind of time series methods are really kind of playing to the strengths of Earth Engine, which is this sort of big data raster style analysis. So that's why I think this stuff is useful. There are limitations. And so we can talk about auto-regressive models, but it's going to get a little sketchy, as you're going to see in a second here. So what does this auto-regressive model look like? Any questions about the cross-correlation stuff before I go crazily down the rabbit hole? Okay. Autoregressive models. We have a pixel value at time t, and that is a function of a constant, and the 2 previous time points. So the pixel value at time t minus 1 and the pixel value at time t minus 2 plus a random error term. And again, we want these betas for every pixel. Somebody was asking me about this yesterday, I think. Is that person here? Yeah, okay. So this is how you do this. And I told you it was going to get nasty. But let's see what happens here. First, what we want to do is lag the collection. So that just means storing the t minus 1th image and say the t minus 2th image in that list on each image there. And now what we want to do is we want to just map a function over it in order to see the number of images that are in that little list, and specifically call it n. And we need n to be greater than 1 because our model is a function of the 2 previous images. And if there aren't two previous images, for example, at the start of the series, or for example, if you've masked out a data point with a cloud mask or something, we can't fit this model. So we need there to be two previous images in there. And here are the independents. We have a constant, and we have NDVI at time t minus 1, and we have NDVI at time t minus 2. And now we're just doing linear regression on this stuff. So we're going to take the independents, add the dependent band, and reduce it with the linear regression reducer. And we have this number of independents. It's 3. It's a constant. It's time t minus 1. It's time t minus 2. And we have one dependent. It's NDVI at time t. And then we do our little dance here. We get the coefficients out. This is a 3x1 array. We use array project to turn it into a length 3 vector. And then we use array flatten to turn our length 3 vector per pixel into a 3-band image. And we just name the bands after these independent variables. Oops. Now, in order to compute the fitted values, we're going to map another function over this thing, but instead of using that, somebody was asking me about the sum reducer there. You know, we had the image.select independence.multiply coefficients.reduce sum, that whole thing. Instead, we're going to use an expression for that. And specifically, our expression is just going to be this, our autoregressive equation, beta 0 plus beta 1 times p1, which is a pixel value at time t minus 1, plus beta 2 times a pixel value at time t minus 2. And the second argument to image.expression is a map, a variables map. And so we're saying p minus, the p1 variable is equal to NDVI at time t minus 1. The p2 variable is the NDVI at time t minus 2. Beta 0 is the coefficients.select constant. Beta 1 is coefficients select NDVI underscore 1, and so forth. And that's just implementing this equation. Now, any questions about this craziness before I go on?
One question.
Yeah.
So what if 1 pixel is masked? You're having 2 images,
Yeah.
but 1 pixel is masked. You don't really filter that out, right?
That is why I am using an expression here, because those pixels will just get dropped. Yeah. Thought I saw another question.
I mean, that's what, yeah, that was the same kind of question.
Yeah, okay. That's the purpose of the expression. Okay, now, there it is. Our autoregressive model applied to the data. Again, this is different if you operate the sample, but obviously this is unsatisfactory. There's tons of missing data here, right? As a result of the, the masking and all these problems that we might have. So we can try to get fancy, and what I mean by getting fancy is using that autoregressive model to forecast, to fill in the blanks here. So here are 2, we can predict this one, then we have 2 here, we predict the next one. Here we have 2, we can predict the next one, and we can keep doing that and try to interpolate on this series. I don't know, is that a good idea? So there's the forecast model. Is that a good model? Maybe, maybe not. You get some really wacky stuff here for sure. Is this thing real? I don't know. Is that thing real? Maybe. If you're, time series people, I'm sure you've got a larger bag of tricks up your sleeves, and You probably have fancy ways of fixing these autoregressive models. But this is how you would implement it in Earth Engine. And here's the complete implementation of this. But watch out, this is, it gets a little hairy, this code here. Okay. We might hypothesize that this is a decent model and it just needs some smoothing to be applied. And pop quiz. How do you implement smoothing with this whole framework? Running median? Okay. That's a good idea. But how do you implement that with Earth Engine? You guys have the answer. Yeah, smoothing, median, mean, something like that. I don't know, some fancy Gaussian function, whatever. But how do we start?
Start with the same lag function, and from that set of images, you get median.
Yeah. So we're going to join the collection to itself, basically. And specifically, we're going to use just a max difference filter. And this time around, we don't care to get just the lagged images. We want the images on both sides, right? Because we have a sort of a sliding window here. You know, our median or our mean function is going to be inside the sliding window that includes, you know, both the backwards and the forwards time direction. So max difference filter, join this collection to itself, and excuse me. Then get the list of images and simply take their mean. I could have used median here if you prefer, but here we just take the mean of all the images in that list of images that have been joined to each image in this collection. And that's it. Easy, right? So in my 2 minutes remaining, I actually finished on time. 2 minutes remaining, are there any questions about any of this, or comments, or concerns, or issues? The question is, are you going to add API sugar to make all this easier? And I think that's the question anyway. Yeah. We have some of those functions.
Yeah.
So for example, there's a, I don't even remember what it's called now. If you look in ee.algorithms, you'll find, I think there's a time sat. There's a, I'm not flashing on the name right now, but there are some of these sort of specialized time series methods. And if there's something in particular that you need or want, let us know. Generally, our approach is if you can do it with the API, then great. And if not, then this is actually a function we need to implement on the back end. And if it gets so crazy that this really deserves some function of its own, then we'll try to do that. But generally, the approach is just show you how to do it with the existing API so that you have complete flexibility. But yeah, it gets crazy. I think the question is, I want to compute cross-correlation from the images, from the pixels of another image that are in my neighborhood, that are in the neighborhood of a pixel. And there are probably a couple ways to do that, and the method that is springing to mind immediately is something called neighborhood to bands. And so that you could do something like compute neighborhood to bands on one image, add that as bands to the NDVI image, say, and then run all the same kind of stuff. That's, again, I haven't thought deeply about this, but just off the top of my head, I think that's. The question is, for the harmonic model, is there a way to compute fit or residuals, I presume is what you meant? And the answer is yes. In fact, that is the detrended model that we made. We made that with our linear model instead of our harmonic model, but it would be exactly the same method. You subtract one from the other, and then you could compute root mean square residual and so forth from that. Developers list. We just moved to a new bug tracker. I'm not sure if you can submit a bug or a feature request on there. Does anybody know? The dataset request link from the help button will take you to this system, and I think you might be able to submit a feature request there, but I'm not entirely sure. But you know, the best thing is the dev list, because then we can say, oh, we already have that, here's how you do it, or more users can chime in and say, I want this too. You know, that helps us quite a bit to prioritize. Okay, I think we're done. Thank you.